Welcome today. In the recording you learned about decision trees. And decision trees, like basically all machine learning mechanisms, are prone to overfitting. And we have to fight this overfitting in several ways. The first way to overfit will be that when we choose between different attributes, then we can achieve the largest gain in information when we choose an attribute that is very fine-grained. An extreme case is that every of our training examples has an identifier which is different from all the others. Then for 100 training examples we have 100 identifiers. Obviously, if we put all of them into a separate node, we'll have a perfect classification. That will not be a good classification, right? It is not a very good property of the tree to have a fan out of 100 at this point. And of course, this particular attribute would also not lead to any reasonable classification. Okay, so what we want to have are attributes that allow us to select, but we don't want to favor attributes that have a very high fan out. Object ID is one. I mean, we could also have a very precise measurement of height of a person. Then probably all of us are a slightly different height, yeah? But that would not be a very good way to split our space. So we need further considerations beyond the considerations that we did in the recording. So one simple consideration is to say we normalize with regard to the entropy of the values of our attribute. So the idea is that if we have a very broad fan out, if we have very many different attribute values, then we will achieve a very high entropy. And we moderate the information that we gain by doing this split according to this attribute by the entropy that arises just from doing this very split. And what we have then, instead of the information gain that you saw in the recording, is that the information gain of an attribute that you achieve is moderated or normalized by the entropy of this very same attribute. And of course, the entropy is just described by the usual formula where we look at what are the values of our attribute, and when we have very many different values, and assuming here that these values are furthermore rather uniformly distributed, then we will achieve a very high entropy. And if you have a high entropy, then the information gain ratio is reduced compared to the information gain. And if the entropy is not so large, maybe we just have two values of equal probability, then we would just divide by 2. So let's use the gain ratio instead of the information gain for deciding on which attribute to use. An alternative to notation to what I just said is that we talk about EDT as the entropy of the distribution and delta IT as the information gain, and then the information ratio is just described by these two formulas. But that's just a slightly different notation than on the slide before. Let's just take a look and apply this to our mushroom dataset. Here we have the root node and we have an attribute cap shape. And we have here for the cap shape the different values that are applicable, and we have accounts, how many of them are poisonous and edible, what is the associated entropy that we gain if we distinguish according to these 4 values in the corresponding subnodes. And the expected entropy that we would get by weighing over these 4 would then be an expected entropy of 0.565, 29 times 0 plus 14 times this plus 3 times 0 plus 45 times this, and then divided by the overall number. gives us an expected entropy of 0.565, and compared to the original entropy, this means an information gain of 0.176. Now, when we take the entropy of our value distribution into account, so how much information do we have when we know how many are this and this and this or in this bucket, then the entropy of this value distribution is 1.54, and we divide this information gain by this entropy to end up with an information gain ratio of 0.114. And we would do the same thing for other attributes like habitat, and might find out that here we have a larger information gain ratio. Of course, same for gill size and so on, and then we can really decide on what to do and use the attribute gill size split according to the two gill sizes that we have, and then create corresponding subnodes and repeat the same procedure as we did when we applied just information gain and not information gain ratio. The algorithm, however, will still be prone to overfitting. Namely, what we do here with this procedure is that we refine our tree further and further and further until we do no more errors. Let's, for example, look at this picture. It's like an artificial picture. We have two classes, these circles and these crosses. So we have two attributes, x1 and x2, and every example here is either belongs to the class cross or to the class circle. And now we try to create a classifier. I mean, what you should see immediately from this picture, without considering any learning mechanisms, is that, of course, the base error will be very high. Remember what the base error was? Well, that's an obvious question for any oral or written exam. Yeah, what is the base error? What is the definition? So the base error was a probabilistic classifier that is optimal, and given that it's optimal, we still have the uncertain, or we still do mistakes, because when there is at a certain data point a probability larger than 0.5 that it's one class, then there could still be the second class with a probability larger than 0 occur at the same point. And that's, of course, what happens here. Like here we have examples that are, well, basically the same, and so they will have a probability to belong to one class, but there is a non-negligible probability that they belong to the other class. And obviously, whatever decision we do, we are prone to making sometimes a mistake when we have a new unseen data point. And that's our base error that we do. Still, when we give such a training sample to a decision tree, then the decision tree will refine ever more finely until maybe just individual data points are in specific nodes. So we reduce the training error by creating a very deep tree until the training error is 0. And the tree will become very complex, and we will overfit to our training data. What does overfitting in this case mean? It will be very specific to the data sample we have drawn from our data distribution. Yeah, every time when we do learning, we have some distribution for one class, another distribution for another class. Now we sample, which is never a perfect sample. It's never, well, it's always finite sample that we have. And depending on the finite sample that we choose, we do some mistakes. And we optimize our model not according to the infinitely large distribution, which we cannot know, of course, but we optimize our model according to the finite sample that we have and overfit to the particular sample we have at hand. So there we run into overfitting. And the problem is that when our training error goes against 0, our generalization error does not. If this picture, I mean, you can recognize a little bit, there seems to be some sort of center for circle class here and there, and the rest is mostly this broader cross class. Then when we train a decision tree with the method that I've described so far on it, then the training error behaves like the following. We have initially one node, and we have a large training error. This training error has just to do with the number of decisions we make. Obviously, we can always say everything is a cross. Then, of course, we have only a mistake for these 1200 and not for the 1800 examples. So most of the time we're correct. We're just having this very simple base judgment, which is not a judgment. It's just like what is more frequent. Okay, so that's our initial error that we have. It's a bit below 0.4. And then as we grow the tree, we reduce the error because we sort our examples into subnodes and subnodes and subnodes that become purer and purer and purer. And we continue to do so until at about 230 nodes, all our examples can be correctly classified as they are alone, maybe in such a node, or well, not completely alone, because in 230 nodes we cannot fit the 3000 examples, but we have a very small number of samples for each node in average. Okay, so our training error is 0. Is this perfect? Of course not. Actually, when we look at the test error, when we do a split, so we do not train on all the data, but we take 30% training data, for example, in this example. So of 3,000 examples, we take 900. We train on these 900s, and then we evaluate how good we are on the other 70%. And then we do this for every tree size that we observe here. And initially, as the tree grows, the test error for these 2,100 data items goes down. But after some time, it goes up again. And that's exactly the overfitting that we do. We overfit to particularities that we have observed. And we are very far away eventually from our training error. So our test error has nothing to do with our training error anymore. And with this very large tree, the test error is even substantially larger than the one we had with a much smaller tree here. So you see 0.32 or something like that instead of 0.24. So what we did, that we grew the tree further and further and further, adapted our tree to the particularities of our data samples, but it did not lead to a good model that would give us good predictive power. How can we fight this? We can try to estimate the generalization error. I mean, usually when we compute the errors, what we do is we have a set of data samples, we select an attribute, then we classify, and we look then when we have these branches in our tree. So here we have a node, then we have 3 branches, 3 lowercase t's, and we count the errors that we do here. So here is 1 error away from the majority class. Here we have 2 errors away from the majority class. So we count 1 plus 2 plus 0. These are the 3 errors that we make here. And we divide by the number of training instances. These are 18, so 3 divided by 18, and 1/6 of them are, that's our error rate. Now, every time that we specialize, we can say every specialization should also be punished, because we risk becoming too specifically adapted to our training data. So let's punish our mechanisms by counting not only the errors that we make. This number gets smaller and smaller and smaller as we refine our tree. But also, every time that we create such a new tree, let's add some parameter lambda as a kind of virtual punishment for enlarging the tree. So every time we do that, here we have this 1/6 error rate, we add this lambda, and when we have 3 such subnodes, that means for a lambda of 0.5, we add to the 3 1.5 virtual errors. So we have 4.5 divided by 18. This gives us then a larger error rate of 0.25 instead of the 0.16666. So what we do here is we regularize. Remember how we regularized with linear regression? We punished overly large parameters. What do we do here? We punish overly large trees by adding these virtual errors on top of our evaluation function. And when we do this, we will end up with a situation where adding more nodes will worsen our error rates. And therefore, we should then stop expanding the tree any further. We can do this during the construction by taking this regularization into account and saying, okay, have we actually achieved improvement or not? We can also extend our criteria. We can require a minimum information gain. So to say, when we go from one node to the next, it doesn't make sense to improve an information by a very tiny amount. And we could also require that there are a minimum number of instances in such a node. I mean, when we take this example, these are very small number of instances. It's probably not reasonable in most situations to deal with such very small sets. Maybe we should rather stop here, though of course this one is rather impure. But I mean, you know, these examples are always tiny for you to look at. In reality, the number of data instances that we talk about in such a situation is always much larger. So this is something we can do during construction. So we can check before we expand, how many instances do I still have? Does it make sense to expand? When I expand, how is my error rate worsening or getting better? With regularization, I can also build the whole tree, which is very broad and deep, and then post-process the tree. Actually, many old previous mechanisms did exactly that. They grew the very large tree and said, where should I cut the tree? So they do post-processing, they remove nodes and avoid excessively deep subtrees. We can also try to produce different trees. I mean, I gave you now criteria to build a tree, but we could sometimes go for the second best solution or the third best solution when choosing attributes. And you have to remember that what we do here is a greedy search. We search greedily for the next best attribute. This need not be the optimal attribute in the long run. In the short run, it's just considering one step, it's the best attribute. But when we consider all possible configurations, it could be a suboptimal choice. So we could try to come up with alternative selections and then construct a tree based on these alternative selections. That could potentially lead us to a very different tree And when we have different trees, we could compare which one is better according to several criteria, like, for example, having leaf nodes that are well filled, and of course having a small training error. Now, when I showed you some of these examples, I already took something for granted that I didn't show you. For example, I talked about continuous attributes, but we have not talked about how to handle continuous attributes like the height of a person. Because then every numerical attribute of every data instance will be different, because it's unlikely that there will be exactly two same heights or same monetary values. So how do we deal with such a situation? Well, how do we do the attribute splitting in such a continuous case? Or how do we deal with it when we have a large number of ordinal possibilities? And I mentioned already one problem, which is a high fan out, meaning that I have very many different values for an attribute. And then the one child node per value is not a good idea to have. So what are alternatives? For nominal values, so nominal values are things where I don't have a specific ordering. Yeah, I just, let's say your first names, yeah, could be an attribute which would be a nominal value. It doesn't make sense to compare them, right? There's not a name starting with A is not in any way better or worse than a name starting with B. It is then problematic to do a split because of that. What one sometimes tries to do is a binary split. And then you need to create a criterion on how to put the one kind of values on the left and the others on the right. A binary split would, of course, lead to a binary tree at this point. And the problem is if I have a large value set, like, say, take first name, yeah, some first names will be redundant. There are always some people called Stefan or something like that. So, but others are, of course, can be arranged in different ways. And there are many possible splits to go with first names, for example. When we have k values, then these are the number of possible splits that we could have, and we don't want to explore all of them. If we have ordinal values, then we can use the order to create meaningful splits. So if we have stocks, and the stocks are rated, or companies, and the companies are rated, then we could make some boundary between the better ones and the worse ones. For names, one could take alphanumerical orderings to create a line, let's say at the letter N, names that start with a letter coming in the alphabet before N or after N. With numerical data, when we have certain values, it's often reasonable to just take the mean value between two such values. But of course, the question is, which of these mean values then should we take? We could, of course, decide to go for the mean value of all of these numbers, or for the median of all of these numbers. And what we can also do, what is done quite often, is to use binning. So binning would imply that if I have different numbers, I would provide bins and say, for example, I take all the numbers below 10, all the numbers between 10 and 20, all the numbers between 20 and 30, and so on. And then I would create bins for these numbers. And here I would need then 3 bins, 0 to 10, 10 to 20, 20 to 30, 3 bins. And I would put corresponding values into this bin, and I would have a fan out of 3. I would distinguish 3 different child nodes from a parent node. What can happen then is that some of the bins are super busy, and some of the bins are hardly populated or not populated at all. That's something you see here. When I create bins, so the bin from 0 to 10 would just have 1 inhabitant, but the bin from 20 to 30 would have all these numbers. Well, it depends on where I put 20, but let's say we include that. Then this would be a very much populated bin. And this is expressed here, that you have bins of equal size in terms of the value range that they cover, 0 to 10, 10 to 20, 20 to 30. This would be fixed width bins, but the number of samples in that bin would vary greatly. Some bins would be busy, like this one here, and some would not contain any instances at all. So an alternative then is to adapt the bins and to say, in those areas where there are many values, I make small bins, small in terms of the size of the values, that how they differ. But because there are many in them, this small size is well populated, and the absolute number of instances in this kind of bin is then determined by the width and the height, so to say, with the idea that all these bins have an equal area, that when I count the number of instances, I always end up with approximately the same number of instances. This gives me quite a well-balanced distribution. If every area here is a child node, then in all the child nodes there are very similar number of instances. That's often liked a lot. So binning is such a technique, both this technique as well as this technique, that plays a major role in many machine learning tasks. Okay, so this is how we can handle also numbers by creating such bins. Then when we look at decision trees, what is good or what is not so good about them? Well, we have the advantage that we can interpret a decision tree. We can, for every new instance, just follow the path through the tree and understand why a new instance, previously unseen, was classified as it was. Now, when we have a medical problem, as a doctor, I could follow the path and say, okay, this is considered a tumor because it has the patient is so old, because the shape of the cell is like this, and because of some other attribute is like that. So I would get a description of why it is classified in a certain way. It is non-parametric. I think we have not discussed that very much, but sometimes we use parametric distributions like a normal distribution in order to produce a machine learning classifier or regression. And when we look at for example, a normal distribution, remember, a normal distribution is characterized by the mean value, mu, and by the covariance matrix, the sigma. And together we have uniquely described such a normal distribution. This, of course, means we assume that our data has a particular shape. We assume that our data distribution is shaped like this. And we only have to find the parameters. And this is then a parametric approach. We assume a certain shape and find the parameters. When we do linear regression, we assume that the shape is linear. Well, maybe we use even some quadratic aspects and find then the parameters for this quadratic representation. But we assume that our data is like that. In a decision tree, we make no assumption. The data can be any shape, and we do not just find parameters for predefined expectation, but it could basically be any shape how our data comes from. Any shape is a little bit maybe saying too much, because the way we separate our space is by decisions that are perpendicular to our axis. So if we have data described in some way, and here we have data points, every decision is like cutting perpendicular through our axis. For example, we make a decision, if this was 2, whether a value was less or equal than 2 or above 2, right? And the same, of course, here. We always do such kind of rectangular decisions when we split a node. But it's not parametric in the sense of having a predefined expectation of how our data is shaped exactly. When we have when some data is missing, this is a problem when we try to model data with normal distributions, because what would it mean that I don't have an attribute value for a normal distribution? It doesn't work, right? I have to postulate something. For a decision tree, I can just say I have a bin for my unknown values. And if something is unknown, it falls into this bin. And sometimes the fact that I don't know a value has a very large predictive power. Maybe my customers did not want to tell me that they have some debt, and therefore I might not trust them. So this kind of information, something is missing, may be very valuable when I want to predict something. It's a low complexity. So prediction is O of L, where L are the number of attributes. So my tree can never be deeper than the number of attributes I have. And quite often it's less than the number of attributes. So that's good for prediction. It's invariant to feature scaling. So when we consider, for example, income, annual income, it's my favorite example always for issues with scaling. This example with Bill Gates or Zuckerberg, and their yearly income, which sort of like pushes all the mean in this room far beyond what we could ever dream of. Then we don't have a problem with decision trees when we have such a feature which is very large out there. We don't need any normalization, which we might require for modeling such data with a normal distribution. Well, we can handle heterogeneous data. So when we have different types like nominal data, ordinal data, numerical data, it's no problem to have them all together. So there are many advantages. The disadvantages I mentioned already, that the splits are aligned with regard to these axes. So I always do a split of my data like this. I cannot have a split that would work like this, which I would sometimes like to have. And I might cause overfitting. So decision trees tend to overfit, especially if I don't care very much about regularization. Okay, yeah? So what would be the advantage or disadvantage if we did? Well, the question is, what would be the advantage, disadvantage? If we would normalize the features, the normalization changes the position of the features, but not the ordering. And in decision trees, all we care about when we look at an individual attribute is the ordering, right? So what are possibilities? So let's look at let's look at income. Just one attribute, nothing else. Okay, and here we have 10 to the power 9 euro per year. Yeah, some Zuckerberg Bezos, whatever, right? So we have a data point here. So now all our annual income is somewhere here. Because compared against the 10 to the power 9, I do a bit better than you, maybe, but I'm a bit older. But still, it's also like here. Now let's assume my income would be here, which is an exaggeration. But let's do a normalization. So a typical normalization for such a distribution would be to take the logarithm. Let's take the logarithm for the basis 10. Then, of course, this person with $1 billion a year income would end up, well, should I do this? Let's do it here, at 9, right? Because the logarithm of 10 to the power 9 is 9. And mine would be in the order of 4 or 5, so it would be something like here, and the student might be like 3, so they would be like here in that order, and so the ordering is still preserved. All that you do is that you push them closer apart, further apart, but you preserve the ordering. Normalization, you sometimes map them to between 0 and 1, but of course that would just mean divide by 10 to the power 9. Then all our incomes would be almost 0. What you try to do with normalization or rescaling is you try to push them apart or squeeze them together, and with such a kind of reorientation, now at least there is a meaningful distance between these different incomes that you can better work with. Okay. Good. Further questions about decision trees so far? Okay, then let's continue with bagging and boosting. Who of you knows Kaggle? Okay, very many people. Who doesn't know it? Also, well, half, about half. Okay. So Kaggle is a platform for machine learning competitions, and this is, well, on the one hand, you can compete there, also sometimes earn some money if you win the competition. You can also just compete there for the fun of it. So I know one was a PhD student of a colleague of mine, and he is like Kaggle champion. Sometimes he's number 1, sometimes number 2, which is a very tough sell to achieve. There are very many challenges, and then you can earn points, and it's like kind of like a honorary competition also to be on top of the ranking, like a tennis ranking that you achieve where you're number 1 or 2. And there are very many real-world challenges there. Well, here are some of the most famous ones that are, not all of them are completely real-world. I mean, they have some real background. And here are some very famous ones that are very small, easy to work with, and you can compare how good your modeling skills are compared to other teams. There is a good predefined data set and a predefined test split, and you can compare against the performance of other teams. Okay, now why do I tell this story? Of course, sometimes it might be nice for you to use some data from the platform for a bachelor or master thesis. That's one thing, or for participating and winning money. Or one can also ask the question, which machine learning methods most often win these competitions? And it's not neural networks. So far, bagging and boosting most often win these competitions. So bagging and boosting are ensemble methods. In the past, it was mostly random forest which won the competition, and that's one technique we want to look at today. And boosting is probably something for next week. What people also like to do these days is to use ensemble of neural networks. Neural networks are really strong when you have natural input in the form of pictures, videos, text. Then you always basically these days require some sort of neural representation. But quite often you also sometimes have a neural representation, and on top of that some other model like some boosting model or a conditional random field. And currently, especially when you have tabular data as you find in databases quite often, then XGBoost is a default method to go to. And the other question when you do machine learning is also how much effort do you have to invest? So how much modeling efforts, how much thinking you have to invest? And random forest is one like decision trees where you have to do very, very little and you get very, very far. Even if random forest is not always the best method or tends not to be the best method anymore. And you can just run it out of the box. I mean, XGBoost is also similarly simple to apply. For neural networks, you already tend to have to do more work. And then if you want to do comparisons, it always makes sense to compare against one of these baseline methods that are easy to run, efficient, and have a very good, if not excellent, performance. So what is the core idea that underlies both bagging and boosting? So all the methods that I now described at a height of 30 kilometers. We have seen this formula before. We have a random variable x0, and we ask ourselves, what is the error that we expect? And we described this as the error between our prediction and our ground truth. And when we analyzed that in this slide deck on linear regression, we came up with the fact that this error consists of the variance we have in our data, which is the irreducible error. So we had this assumption in linear regression that we have a linear generating function and some fluctuation on top of that. So that is irreducible error, which we cannot avoid. And we had some bias in our model, our f hat, and we had some variance that also comes from the fact that we don't, it depends on which kind of data we sample. So this is then our prediction error. It comes from these three sources: the irreducible error, the bias, and the variance. And if the variance of a prediction function is very high, like decision trees have a very high variance, so we take data from a distribution, and now we have samples from this distribution, and now our perpendicular splits really depend on which exact data we have sampled. And the way we have constructed the tree really depends on what we have sampled a lot. Then our predicted model f hat will have a high variance with regard to our data sample. And if our function has such a high variance, this contributes to the prediction error. So the idea is that we apply bagging or boosting in order to alleviate this prediction error. And how do we do bagging? It's a very simple procedure. That makes it also so attractive. You have your data samples, and actually you do not just, you have your data sample, and then you choose a set of data samples, subsamples. Then you learn one predictor for each data sample that you have. And then when you want to do regression, you average the results of the predictors. And when you classify, you vote for the classes by the predictors. Yeah? So it's really like you have here some data points. And then you take all this data D and you create subsamples. And for each subsample, you create a new predictor. And then you either average when you predict numerical results, or you just say, what is the class that has been most often voted for by my different classifiers. When you do boosting, you weigh your training data. You weigh your training data in a way such that data that is misclassified the most often receives the most weight. And then you choose a very weak predictor. This is a bit abstract. This is quite clear, I think. This is quite abstract, but when we get to the actual method, it should become clear. But that's about it. It is really about using some data several times. So let's first look at one example of bagging, which is a random forest and how to construct a random forest. A random forest is nothing else than multiple trees, multiple decision trees, right? That's a forest. Forest with one tree is a bit of weird forest. So we want to have more than one tree and probably more than two to have a forest. Good. How do we do this? Well, let's first assume we have them already. Then we just do a majority vote if we want to classify. Right? So we have 1, 2, 3 trees. When a new instance comes in that we want to classify, we let the instance be classified in all the 3 different trees, and then we check what is the class predicted here and there and there. And then we do a majority vote. That's it. Now, why is this a good idea? Let's assume this idealistic hypothesis. Let's assume that our trees are, every experiment, this is a little bit an important but unusual way of thinking. Every experiment that we do is itself like a sample from a distribution. Like even when I measure a certain height, let's say I want to measure from the floor to this point here, and I do this several times, every time is like an experiment. And every time I get a slightly different result. And I will do some mistakes, sometimes because I'm sloppy, because I have not a very accurate ruler, whatever. Because my ruler isn't exactly perpendicular to the floor. So every time I do such an experiment, I will produce a result which comes from a distribution. When I construct a tree which is based on data samples, every tree I construct also comes from a distribution in the end. It's a complex thing. We are used to having values coming from a distribution, but a very complex object also comes from a distribution. And so every time I do something anew, my tree that arises is sampled from a distribution, and the set of trees that I produce are sampled from a distribution of trees. Now, let's assume they do not correlate with each other. They are sampled from a distribution, but how I sample the first tree does not influence how I sample the second tree. Of course, they come from the same underlying distribution, but and they come from the same underlying distribution means they are identically distributed. But they are independent in the sense that my first measurement, my first tree construction, does not influence my second measurement, my second tree construction. So that means my trees They are themselves values from a random variable. And this random variable has a mean mu. And this mean mu, when I sample from a distribution, is the same mu for 1 tree or 10 trees or 100 trees. When I measure from the floor to up here, the mean value that I expect is the same one, unless I do a systematic measurement mistake, is the same one I get every time. So the mean is not changed whether I do 1 tree or 100 trees. So that means this bias that I get by constructing trees is the same. What is, however, changed is the variance. So initially my distribution has a variance, which I don't know actually, but it has a variance, sigma square or capital sigma, a covariance matrix. I don't know this variance, but it exists. But when I do such a measurement from the floor up to here, and I repeat this, then what I observe will fluctuate around the true value. And the more measurements I make, the more precisely I can say what the true value is. Yeah? So this is what happens when I throw a coin once. I have a 0 or 1. I don't know whether it's fair or unfair. When I throw it 10 times, I might already be closer to this true average value. And when I throw it 1,000 times, I know much better how close it comes to an expected value. So when I have more trees here, the variance that comes from looking at all these trees is smaller. And actually it's very simple, smaller. If I have b many trees, the resulting variance is sigma squared divided by b. So when I sample from these IID distributed trees, I keep my mean value, but I reduce the bias, the variance, sorry. I reduce the variance. The more trees I sample, the less I get. Now, the question, of course, is, are these trees really independent? This is where this idealistic consideration does not hold fully, because my trees come from the same data sample that I have. I have data observations based on which I want to learn. I have nothing else. I mean, if I had more data, that would always be better. Nothing is better than more data, yeah. But I have the same data. So the trees that I will create are not completely independent from each other. This is why they are somewhat correlated. And if I have b many trees that are correlated with rho, then the variance that is achieved is not rho squared divided by b, but it's sigma squared divided by b, but it's sigma squared times this, namely the correlation, plus 1 minus the correlation times divided by b. If the correlation is 0, this formula is the same. But if the correlation is non-zero, my improvement is not quite as strong. So, when I create several trees that are almost or that are little correlated, I get an improvement like this. And that's the idea behind bagging, because I improve this part. The bias was my mean value. That stays the same. And this I cannot reduce anyway. Okay, so what how to do. I choose data samples from the data I have available. I don't take all the data. I want that the data samples on which I build my trees are not exactly the same. Then I learn a predictor on every data sample, and then either average results for numerical predictor, or I look at majority voting to determine my class. There are actually even more aggregation mechanisms. We have a recent paper where we use some social decision theory method, but I mean, this is what is typically done. So random forest is then a method for bagging uncorrelated or almost uncorrelated trees. Well, more specifically, define a number of trees, and then we go over this number. We draw. Now this is more specific than the previous slide, but otherwise the same. We draw a bootstrap sample Z star of size n star from the original data set with size n. What is a bootstrap sample? It's random sampling with replacement. So here I have my data, and in order to create a smaller bootstrap sample, I take this whole data, I take out a piece of data, put it aside, but I also put it in again. It could be that I sample the same data item several times, potentially. Why is this typically done, defined like this? Mostly for theoretical reasons, because then it's easier to derive statistical propositions. Whereas if you destroy the data set, you change the distribution, and then some theorems are harder to formulate. Okay, so we do bootstrap sampling, and this n star is smaller than the n. Cannot really be larger, doesn't make sense to be larger. Then you grow a random forest tree, TB, so this is the index. We grow capital B many trees, but here we grow the first tree, the second tree, and so on, using our current sample. And well, we do this, for example, we just do a decision tree with all the same considerations that I showed you when we handled decision trees, like being sure that we don't do too much overfitting, etc. And what we also do is we do not consider all attributes, but we select a subset of attributes. So we do not only select a subset of data items from which we learn, we also select a subset of attributes. Why? Well, we want to uncorrelate these trees. And well, we use gain ratio, for example, to split the node into children nodes. And here, yeah, the attributes we choose tends to be smaller than the square root of the attribute. So if you had 100 attributes, we would maybe select only 10 of them or 9 of them. And then what we get is not a single tree, but a set of trees. Maybe these trees are even simpler because we have less data to train on and we have fewer attributes to train on. And then when we do a class prediction, we do the voting. How do we vote? Well, we go through all the trees. For every tree we ask, what do you predict? And then if class I is predicted, this is 1, otherwise this term is 0. And so we count for each class I how many of the trees have predicted that specific class. And then we take this class that maximizes the sum of these 0, 1 decisions. So that's then our classifier f hat. And so what about the generalization error of such an ensemble? So the bias of the ensemble is identical to the bias of a randomized tree. That's the same consideration we had before. It is a bit higher actually than if I had taken all the data and all the attributes, because, I mean, this before was an idealized consideration of what we want to achieve. The more we randomize, the more the variance goes against zero when we grow the number of trees. But it's not completely randomized because, well, if we go completely randomized, then of course we lose also the information that we have in our available limited size data set. So what we get up here is again a trade-off between bias and variance. I mean, if we only take one attribute, then of course we have a lot of randomization for each individual tree, but the quality will not be so high, the bias will be rather large. So randomization increases bias, but decreases the variance, and yeah, that leads us to the bias-variance trade-off, similar to what we had before. Advantages for such a random forest? Well, it has a better accuracy than a decision tree. It's rather robust to outliers and missing data. I mean, consider if there's an outlier, you sometimes drop that outlier. If there is missing data, you sometimes ignore that attribute where such data exists. It's robust to irrelevant attributes. Again, it's non-parametric. We don't have this expectation about the shape of our distribution. We have the same invariance to feature scaling and types that we had for decision trees. Random forests inherently reduce overfitting. Even if we generate overfitting trees, with the voting schemes that we have, we will reduce this. Still not a good idea to grow extremely large trees. And especially for large data sets, when we can create meaningful subsamples, then it gives us a high accuracy. I mean, if we have very few data items to train on, then creating subsets of these data sets is typically not a good idea. But if the data set is very, very large, where we even have a problem to consider all data, then it's a very good idea to work on subsamples of the data set and apply such a mechanism. Interpretability is reduced because we can no longer, let's assume we have 100 trees. I mean, in every tree we can go down the path to see why a decision was made, but then it's not one path that we have to go down, but 100 many paths. And so the interpretability is reduced. But we can still look at the interpretation of random forests, and that's what we want to do here. What, of course, would be most interesting here is the attribute importance score. Which are the important attributes for prediction in our random forest? How can we go about that? So we have our bootstrap set, and not every data item is bootstrapped. So we have out-of-bag samples. Maybe we even have a separate set, but at least we have out-of-bag samples that were not used to train a specific tree. And then let's look at the corresponding trees and just manipulate the value of the attribute that we want to assess. We want to know how important is a particular attribute for classifying. How important is it to know the gender in order to determine income? This is something we may want to assess. Then we look at an evaluation metric. We looked at accuracy before. Depending on the problem, it could be something else like precision or recall or AUC. Or that's not something we had, and we look at how does the accuracy decrease when we manipulate the attribute. So this, of course, means that we do a random decision at this attribute and then continue and compare how much worse our test set is treated compared to the unchanged version. And that's the core idea, yeah? Knowing that we do some randomness in the attribute, this helps us to assess how important this attribute was. So the attribute is important, of course, when we lose a lot of accuracy. Then knowing about this attribute was important. So how could this look like? Well, it could mean that an attribute, of course, in one of these trees is in different places. Here the attribute is on top, here the attribute is somewhere halfway there, and here it's lower in the tree. So depending on the individual tree, such an attribute may play a different role, and we have to look at all the different changes of decisions that may come from such an attribute. What is the problem with this? It is expensive. It is expensive to assess something in this way. We do it on a test set and separate, and we have to do it for all attributes. So we have to do it for all attributes, for all nodes, to assess their importance. And we cannot do it during construction. In order to handle these problems, one sometimes chooses, instead of the mean decrease of accuracy, the mean decrease of impurity. This is not the same, right? Accuracy means then eventually that on a test set, which was independent from the data I had, I assess the importance of an attribute. The mean decrease of impurity looks at the construction time and how this attribute led to a reduction of impurity. So we could, of course, also do it at test time, but we can also do it already at construction time. So for an ensemble of trees, P many trees, phi of m, so each tree is indexed with this m, I look at the impurity the importance of such a random variable xj, so this is an attribute, by going over all the trees, by looking at all the nodes in my tree, and for every node, I ask whether this node looks at this specific attribute. Here it might be here or there or there. And I look at what is the probability of ending up here in this node, and what is the impurity reduction in this node. The impurity reduction is something I computed during construction. So here we use the impurity reduction, we don't use the ratio. So here we don't use we don't use the entropy in the denominator, just the impurity reduction. This impurity, of course, looks at, or this impurity reduction, you can use different measures. You can use the reduction of entropy. But what you don't do is you don't divide by the entropy of the attribute itself. If you look back to the slides where we had the two definitions, there are definitely different specific measures. So here we would use, because we looked at this one version, what is the information gain we have? And there are similar measures like impurity reduction that we can use, but you can also look at this information gain here. But not the information gain ratio. And so we look at how probable is it and what do we get here. And when we then look at the importance of these attributes and we sum over all the nodes, and was this a node where this attribute was busy, and how important was this attribute here, then this is what we will measure here. But here, the impurity, here it's defined as impurity, not as the information gain. Is defined like that. What is the impurity of the parent node, and what is the impurity of the left subtree or the right subtree? If we have more than 2 nodes, it could also be this, the third and the fourth subtree, and how many, what is the ratio of instances ending up in this corresponding subtree. So what we end up with then is a mean decrease in impurity. The importance is then measured as described before. The probability of being in a place is how many instances are in a node divided by all the instances. So the intuition is an attribute is important when it decreases impurities. It is used with many samples, and it is used many times. MDA is not used widely because it's very expensive. MDI is much cheaper, faster, and easier to compute. And empirically speaking, there's no proof for that, but empirically speaking, it correlates well enough with MDA. Okay, so then here is one example of a paper that has looked at MDI, and then it found the importance of different attributes. And here the problem was a predictive model for diagnosing some carcinoma. And age was a very important attribute here. And then come some more medical terms, which I don't know what they mean, but you could actually look them up in this source. And of course, you find that some of the measurements don't play any role or hardly any role. What is the computational complexity? When we look at a decision tree, the complexity has to do with the number of instances. And of course, we need to sort the number of instances because we need to do the splits. So when we look at one attribute, we need to sort this attribute. Sorting takes n log n. When I take quicksort, for example, or merge sort. Now we don't need to do this just once, but we need to do it log n many times. So how deep can the tree be? That could be log n deep. We have to do this for L many attributes because every attribute could be the best attribute in a particular node. So this is the component of L. And this is what it takes to compute a particular decision tree. When I want to predict something, I just have to go down the tree. This is much faster. This just takes O of L, where L are the number of attributes. For random forests, I don't take the data set n of size n, but I take bootstrap samples of size n hat. So I no longer have n, but I have the smaller n hats. And I have the subsets of attributes L hat, but I don't do this just once, but I do it b many times. Well, and of course, it depends when I then always work on the full data set. This is what is described here with extra tree, that I keep the n instead of the n hat. Okay, what is the takeaway on random forest? We sample the data. We also sample the attributes. And when you have a new machine learning problem, then always try simple methods first. And random forest is one of these simple methods. Not the only one. I mean, linear regression, etc., is also something that you should do, or logistic regression. So do simple methods first, and then check whether your more complicated methods improve on that. But don't start with the complicated methods. I mean, sometimes people, I read this paper, they have this method, and then this does this and this and this and this and this. And you really don't know even whether you get a good result or whether a simple method would have done better. Now I looked at doing random forest and do the voting for classification. Of course, you can also do this for regression. We did not look at regression for decision trees, but you can do regression for decision trees, and then you would here actually also average the values. So yeah, that's a good and simple method to start with. Okay. Like 2 years ago or so, I evaluated the lecture, maybe something also we should do this year. And some people complained, he doesn't do even explanation, and explanation is so important, without noticing that I had MDI and MDA already in my lecture, which are also explanation methods. But I thought, okay, now people want to have some explanation methods. Let's also do some method that go explicitly under the term explainable machine learning. Even if MDA is already a very simple form of explainable machine learning. Now, what you saw already with MDI and MDA is that we are interested in the contribution of attributes or features. Sometimes attributes and features, by the way, are the same thing, right? When I use an attribute as it is given directly, sometimes I take an attribute and modify it, I normalize it, for example, or I rescale it. Then, of course, we would talk about a feature, not about an attribute. So when I talk here about feature attributions, it assumes I have maybe already taken some steps to modify an attribute into a feature. Maybe I've just taken an attribute as it was. So the best known method these days for attributing the importance of features, either for individual data items or for a whole data set, are Shapley values. The reason is that Shapley values have very nice theoretical properties. The drawback of Shapley values, which you can also see from the formula, is that they are computationally very expensive. And therefore, when we look here at these theoretical formulas, I have to add immediately that in real-world applications, these formulas are not fully computed, but only approximated. But then you have the packages that do this approximation for you. Okay, now what is the idea of a Shapley value? It is not so far away from MDA. It is based actually on game theory. Shapley values were defined, I don't recall now, it was 60s or 70s in game theory. And you can imagine this as, I'm a soccer team manager, and now I buy a new team, a new soccer player. So what is the value of this soccer player? Obviously, if I don't have this soccer player, I mean, typically these teams have like 20 soccer players or 30 soccer players, but only 11 of them run on the green, right? So obviously, you can play without this new soccer player, and this soccer player costs money. So what is the worth of this soccer player? And of course, you have to assess this in a certain way. I mean, you want to be robust. For example, maybe the soccer player is good only if a particular other player is on the field. And not in all other configurations, but if this other soccer player leaves or is has some injury, then the new purchase would also be valueless. So how do I assess the situation that the new soccer player and the value of the new soccer player depends not only on him or her intrinsically, but on the coalition of playing soccer with all the other people on board in every possible combination. And that's exactly what Shapley values try to assess. They try to assess how good is a new instance or an already existing instance, an attribute, a feature, in combination with others. How do we do this? Well, the idea is that if we have such a set of features, now this n may be a little bit confusing because most of the time we use n for the data set size. But here, n is not the data set size, it's the feature set size. So maybe I should have chosen L here. So we have so many different features or attributes, if you prefer that. So attributes from 1 to p, this is the set of features. And now I look at all the subsets of my feature set. I'm interested in the contribution, the Shapley value of my player J. Well, imagine a soccer player. Soccer player J joins my team. And what is this soccer player's value? Here I have to say that this value is based on a value function. And a value function is something which is very hard to do for soccer players actually, but much easier for other mathematical constructs. You take a subset of all features and you map it into the reals. And this valuation function, for example, in soccer, it could take a team of players and compute how many goals it scores or how many goals it scores more or less than the others. So if a certain team scores 2 goals over another team, that would be 2. If the other team scores 2 goals more, then it would be -2. So yeah, you could imagine this as a valuation function. Now for real soccer teams it's super difficult to do because you would have to let them play in all possible configurations. Of course, if there's just, this has to be done for all subsets. So it also has to be done for a team of size 1. Now if a team of size 1 plays against a team of size 11, maybe they wouldn't score so well, but even then, if this person gets fewer goals than another person, maybe that's already quite good then. Okay, so this is a valuation function. Now, this valuation function could, for example, be the accuracy of the approach. So I want to say that when I take a set of attributes together, I get a certain accuracy. And now what I do here is I look at all of the subsets that do not include the new soccer player, and I look at the valuation function once with this soccer player and once without. Basically looking at what is the outcome of the game with this soccer player included and without him or her. And for soccer, this would be the difference in the number of goals when I add this player. And in machine learning, it would be what is the accuracy when I include this attribute versus when I don't have this attribute. Now, this is for a specific subset, but I do this for all possible subsets that don't include J, because J is included here, but not there. Now there comes a specific trick that one has to consider. Namely, in how many ways can I put together a team? So, you know this from sports in high school maybe. At my times, at least one person was chosen to choose all the others. Yeah, and that would go. I was chosen almost like the one but the last. So I'm a very bad soccer player. So, but still, you can compose the team like by having a person on the first position or on the second or on the third. And when you look at all the different positions, then you get different the same team in different ways. And how many variations of the same team can you get? Well, this is described by this formula. You describe basically how many ways can you choose the team players that are in, how many ways can you choose the team players that are out, divided by how many configurations. This, by the way, is the same formula as if you have a lottery, 7 out of 49 or something like that. Yeah, because 7 out of 49 means, or 6 out of 49, 6 numbers are chosen. This would be here. 6 out of 49 means 43 numbers are not chosen. These are here. And then you have how many orderings can you put these numbers into. So this represents all the many different ways in which you can arrange the same choosing of the subsets. So you take the difference, the accuracy gain that you get by having this additional attribute, and you multiply it with the different ways that you can pick this particular team, this particular attribute set. And this taken together gives you a Shapley value. So basically you have looked at this attribute in all possible configurations, weighted with how often such a possible configuration could be chosen. And this Shapley value for a particular attribute has some very nice properties. For example, it looks then, for example, when how should I say this? When the player offers no contribution, yeah, this is directly measured and visible by this way. So one property is the efficiency property. What is the Shapley value? When I take all the different attributes for my function f at a particular data item point. So this is nothing else than this function value at this point minus the expected value of the function over all data items. So basically, when I consider the Shapley values for all my attributes, then they describe my function aside of some mean value. So with the Shapley values, I can calculate how my attribute helps to push a data item towards the prediction. I also have this uninformativeness property. And the uninformativeness property says a feature J that does not change the predicted value has a Shapley value of 0. So whether I have this team player, this attribute, or not, does not lead to a different contribution. And this is just a pointer to some nice website. And this website classifies text into being more positive or more negative. And here I gave a little bit of offensive text in. This website is fucking cool, damned. And the funny thing here is it basically gives you an impression how positive or negative an attribute, here the attribute is the word, in a certain context. And yeah, you would see here some output. Fucking cool is a positive output, benign. And when I add the word damned here, then it's toxic output. And you basically see which words here are positive in red and which ones are negative in blue. And when you add these values, you end up with the expected value up here. So I thought this was a nice visualization of the Shapley values underlying this. Forgive my offensive text here. Yeah, it was just very nice to illustrate this. Okay, that's it for today. And yeah, maybe next time I also talk a bit about a current PhD student who just finished and who uses that Shapley values.